In this video, we will talk about what a combination is. So I want to begin with an example, which says that a committee of 3 people is to be selected from a group of 25 people. How many ways are there to do this if, in part A, the committee will have one person be the chairperson, one person be a media specialist, and one person be the research head? So I want to begin this question by giving you all the opportunity to try this. So pause the video for 2 minutes to try this question. This is actually a review from our last section. 4, 3, 2, 1. Pause the video. Pause it for 2 minutes to try this. Alright, so hopefully you've done that. Hopefully you paused it for about 2 minutes to try this question. Alrighty, so the first thing that I want to notice about this is, we're picking these 3 people to form this committee, and they're going to occupy these 3 roles. And these roles are different. So there are different roles. So if we were to choose these people sort of one by one, the order that they're chosen in matters. For example, if I put the first person in the chairperson role and the second person in the media specialist role, the order in which they're picked is going to matter. And we saw in the last section that that corresponds to a permutation. So if we want to count the number of possible committees in this example, well, there's 25 ways to choose the person for the first spot. Let's say we pick the chairperson first. 25 ways to choose them. And then once we have them chosen, so in fact, let me just write down that I am going to pick the chairperson first. And then after that, maybe we'll pick the media specialist. And then after that, we'll pick the research head. All right, so there were 25 people in this group initially, so there's 25 choices for who can be the chair. And then once we pick the chair, now there's 24 people left to choose from to fill this media role. And then once we've picked both of those people, the chair and the media person, there's 23 people left to occupy that research role. And if we multiply these numbers, we get that this equals 13,800. All right, so that is our answer actually. So I want to recall a bit of notation. This is, we would write P of 25, comma 3. Remember, this notation means the number of ways from a group of 25 people to permute 3 of them. And let's also recall that this can be written in that factorial form as well. So remember, the formula for this was you do 25 factorial over 25 minus 3 factorial. So 25 factorial over 22 factorial. And that's the same thing. It's the same thing as what we had above. All right, so now I want to put a wrinkle on this question, which is part B. Everyone on the committee now has the exact same role. All right, so let's talk about this. So for part B, it's not just 25 times 24 times 23 like we got for that last part. So why is this? Why is it not just the same thing as what we had before if the roles are all the same? Well, to answer this question, let's say that A, B, and C, let's just say that these are the names of people, are chosen. I'm just going to label these people as A, B, and C. So if we look at the value we had before, 25 times 24 times 23, this implies the order in which these 3 people are chosen matters. So it counts A, B, C, being picked in that order, as being different from rearrangements of those three letters, like BCA or CAB. So it's counting these rearrangements of those same three letters as different. Okay, when they are still the same committee in Part B. So simply put, the issue with this initial count is that it overcounts. This is bigger than the actual value we should be getting. So I'm going to put a sad face here. So we're not totally happy with that. But as we saw in the last section, we have a method for dealing with this overcounting. So if I look at, this selection of three people, like let's say I had A and then B and then C picked, we can think about how many ways there are to permute these three objects. So these can be permuted because we have three objects. We can permute them in 3 factorial, which is 3 times 2 times 1, or 6. 6 ways. Okay, so overall, what's happening is, I'm going to put an implication arrow. So this implies that 25 times 24 times 23, this counts each 3-person committee (3 factorial, which is 6 times. So it's counting every single committee way too many times. But because we know how many times it's counting that a 3-person committee for each 3-person committee, we fix it by just dividing. We're going to divide by 3 factorial. Okay, so that will give us a method for our answer. So what we're going to do is take our initial count, 25 times 24 times 23, and divide it by 3 factorial. And if we work this out, this ends up giving us 2,300. And that's our answer. So just like with permutations, there's a way to write stuff like this purely in factorial form. And that's what I want to do next. So let's think about another way we could write our answer. So we had the value 25 times 24 times 23 all over 3 factorial. So let's multiply the top and the bottom by something so that the numerator becomes a perfect factorial. So to complete the factorial on the top, I would need to start to multiply by 22, and then times 21, times 20, times ... until I finally get down to times 2, times 1. So whatever I multiply by on the top, I got to do the same thing on the bottom. So I'll have times 22, times 21, times 20, times ... times 2, times 1. And now simplifying this, the numerator is now just 25 factorial. And on the denominator, we actually have 2 different factorials. We have that 3 factorial first, and then times 22 factorial. So this is another way that we could write our answer. And as we'll see, this form, the purely factorial form, will be helpful when the numbers are large. It'll help us just concisely write our answer. All right, so now we are ready for a definition of this thing that we introduced in Part B that we've been counting. So the definition says that a combination is a selection of k objects from a set of n objects where k is less than or equal to n, where the Order does not matter. And we're going to have a notation to refer to the number of combinations. So we are going to let C parentheses n comma k, or sometimes I'll call this C of n comma k to use function notation. This is going to be the number of ways to select a combination of k objects from a set of n objects. So to recap a little bit, with combinations, when we're picking our k objects from the set of n objects, the order does not matter. And that's why we had to adjust for the overcounting. With permutations, which we talked about in our last lecture video, the order in which we picked the objects did matter. So that was like part A in the example that we did here. The order did matter because the people being selected were filling different roles. Okay. All right, so let's go back to where we are in the definition. So there's one other really commonly used notation instead of C of n comma k to refer to the number of combinations. So I want to show you what that is. So we also write C of n comma k as, we kind of put these big narrow parentheses, and then we write n on the top and a k on the bottom. So this is not a fraction. It's a big narrow parentheses, n on the top, k on the bottom. And the way I say this in words is we say n choose k. So that's some terminology and notation that I'm going to be using often when we talk about combinations, just because it's so commonly used in math. All right, so in the first example, in example 1, part B, we found the number of combinations picking from a group of 25 objects. The number of ways to choose a selection of 3 of them where the order does not matter. So let's practice using this notation. We can also write this with these skinny parentheses and put a 25 on the top and a 3 on the bottom. So I say this in words as 25 choose 3. I can think of that as I'm choosing 3 objects from a group of 25. And what did this equal? Well, it was 25 times 24 times 23. Then we divided by 3 factorial. And when we worked it out, we got 2300. And that was our answer. So in terms of our goals for this section, we finished goal number 1, which is defining and counting combinations. We'll actually continue talking about this first goal in the next video a little bit more. We'll actually find a general formula to count the number of combinations. In this video, we've also talked about our second goal, which is talking about when do we use permutations, aka when the order matters, versus when do we use combinations, and that's when the order does not matter. So in the next video, we will talk about finding a formula to count the number of combinations.